Okay, so we're going to start the course material. Let's start with the course title again. So this is a course on officially on cardinal arithmetic. Master's level course. The cardinal arithmetic, I think, is an interesting subject, but it's very specialist. It doesn't have that many connections with the rest of mathematics. But cardinal arithmetic is part of a larger subject called set theory. And set theory has very many connections with the rest of mathematics and is a very important area of mathematics for a number of reasons. So in spite of this being the official title of the course is mainly going to be about set theory. But the theme of cardinal arithmetic is going to be part of what we cover, part of set theory, and it's going to be something we'll return to at several points during the course with more tools at our disposal. And it's also a good starting point for the course because cardinal arithmetic and set theory essentially grew up together. They were developed at the same time in the 19th century, so the 1800s by Georg Cantor. Cantor developed the basics of set theory, like the basics set theory in the 19th century. Because at that time, many mathematicians had realized that having some notion of set was an important abstraction to have available in mathematics. And Cantor became very interested in notions of size of set. And one of his famous early results, was that the set of integers, or the set of natural numbers, if you like, let's use the set of natural numbers, has a different size from the set of real numbers, which he formulated like this. There is no bijection between set of natural numbers and set of real numbers. Because obviously the set of natural numbers embed in the set of real numbers, he took this to mean that the set of real numbers has a strictly larger size than the set of natural numbers. So the set of real numbers, they're both infinite sets. This is a countably infinite set. We can count our way through it, but this is not a countably infinite set. So there exist sets that are not countably infinite. So R, the real numbers, is an uncountable set. So then Cantor asked a natural question, which is, well, we have an uncountable set here. The natural numbers are a subset of it, so we have an uncountably infinite set. The natural numbers are a subset of it, so they're a countable infinite subset. We know we've got two different sizes of infinity here because we know we don't have a bijection between the natural numbers and the whole set of the real numbers. We can ask the question, if we take an arbitrary subset, an arbitrary infinite subset of the reals, will it always be the case that we can either put it in bijection with the natural numbers or with the real numbers. And for all the sets of reals, infinite subsets of reals he could come up with, he could always do that. And it seemed like a general property of subsets of the reals, so he proposed that this should always be true, but he could not prove that this is always true. And this is the famous this property is the famous property that is now known as Cantor's continuum hypothesis. So the continuum hypothesis of Cantor is abbreviated CH. So we can state it like this. Every infinite subset of the real numbers is either in bijection with natural numbers, so it's countable, or in bijection with the reals. And as I said, Cantor couldn't prove it, and nobody else could prove it either, and it became a popular thing to think about or try to prove, especially after Hilbert, the very famous and brilliant German mathematician who, at the start of the 20th century, so in the year 1900, at the World Mathematical Congress, or whatever it's called, proposed a list of challenge problems for mathematics in the 20th century. Very famous list of, at the time, open questions. And the very first question on his list, so this became popular as Hilbert's first problem. The first open question to solve was, does the continuum hypothesis hold? So is it true that every infinite subset of reals is either in bijection with the natural numbers or in bijection with the real numbers? And then, during the 20th century, no one was able to prove it. And Kurt Gödel in the late 1930s realized that actually he could at least prove that from the axioms of set theory, you can't disprove the continuum hypothesis. It's not possible to, he could prove that it's not possible to prove the negation of the continuum hypothesis from the usual axioms for mathematics, the axioms for set theory. So another way of saying that is the continuum hypothesis is consistent with the axioms of mathematics, but still that doesn't mean it's provable from the axioms. And quite some time later, in the 1960s, Paul Cohen finally proved that actually you also can't prove the continuum hypothesis from the usual axioms of mathematics, from the axioms of set theory. So we can now prove that from the axioms of mathematics, which are the axioms of set theory that we're going to talk about, neither the continuum hypothesis nor its negation is provable. Okay, so in some ways it's a question that you can't settle, at least not unless you accept other different axioms of mathematics. And nowadays, most people basically believe it's not really a kind of mathematical question that has a definite answer. You have it one way or you could have it the other, as those results of Gödel and Cohen show. But some people believe that there is one true set theoretic mathematics, and in that one true set theoretic mathematics, the continuum hypothesis is either true or false. But we really don't know that. No, we really don't know at this point which one it is. But maybe we shall at some point discover some further axioms that we will see that they are true axioms, and those axioms will enable us to settle the continuum hypothesis. So I don't want to. This course is not going to dwell very much on the philosophical side, but it's interesting to consider these questions. And because this is the first lecture, I've put a link on the web page to sort of philosophical paper by Gödel, which is, I should have written down the title. Actually, I've got it in my notes, but anyway, something like this. So there's a paper of Gödel's called What is Cantor's continuum problem? And I strongly recommend you have a look at this article to see that Gödel is a brilliant person. He writes very forthrightly from the point of view of someone that believes deep down that there is one true mathematics out there, and the continuum hypothesis is either true or false, but we don't know yet. At this point in the course, it will be quite a challenging read to understand this article, but I suggest you have a look at it. And then I suggest at the end of the course, you come back to this article. As I say, the course is not really going to be philosophical, but at the end of the course, you come back to the article, and then at that point, you should have the knowledge to be able to understand the article much better. Okay, so right from the start, there was a question about Cantor was interested in different sizes of infinity, and one of his mathematical contributions includes introducing a notation for talking about the sizes of infinite sets. And this is how we draw an aleph. I hope I've got it right. So we have the aleph notation. Of infinite set. In which the smallest infinite size is the size of the count of the infinite sets. So that's aleph 0. This is count of the infinite sets. And the next largest infinite size, well, we just increase the index here. So we have aleph 1. So this is the next largest size of infinite set. And strictly speaking, this is the size of the cardinality. And here we're going to use the concept of a well order, which we'll introduce quite soon in lecture 3 of the course. Those of you who, probably most of you who did logic and Nojice in the first year will maybe remember the notion of well order from that course. But this is the cardinality of the smallest uncountable well order. Well, what's the precise definition? And then we can increase this index here to get larger and larger sets. And what this index is, aleph, in general, we have aleph alpha, where alpha is something called an ordinal. And ordinals are another notation system for infinite sets, especially for these well-ordered sets. So Cantor also introduced the notion of ordinals, a measure of the order type, as it's called, of a well-ordered set. So he was a very creative person, Cantor, so he introduced basically two kinds of ways of manipulating infinite sizes: cardinalities with the aleph notation and ordinals. And using a mixture of the two, so the aleph notation depends on the ordinals in order to be able to use it. And then we have a way of talking about the size of the infinite set. And in fact, the continuum hypothesis can be reformulated as a property talking about as an equation in the arithmetic of cardinalities. So I want to just present that formulation now. So we also have another version of the continuum hypothesis. So here we're talking about, does there exist, so the continuum hypothesis postulates that there does not exist any infinite set, that any infinite subset of the real numbers that is neither in bijection with the natural numbers nor with the real numbers. Namely, there does not exist an infinite subset of real numbers whose size is somehow strictly between those two sizes, the countably infinite size and the size of the continuum. So the continuum hypothesis can be thought of as saying that the cardinality of the real numbers is that of the next infinite cardinality beyond the countably infinite one. In other words, it's aleph 1, because that's the next size of infinity up from countable infinity. So the continuum hypothesis can be just written as the equation saying that well, let's put it this way around. The cardinality of the real numbers, well, where does the cardinality of the real numbers lie in this aleph notation? Well, we can get it using arithmetic operations on cardinalities. The cardinality of the real numbers is, cardinalities support operations of sum, product, exponentiation. And the cardinality of the real numbers turns out to be 2 to the power of aleph 0. And the continuum hypothesis is saying that that is the smallest cardinality of an uncountable infinity. So it's saying this is aleph 1. Okay. So with this cardinal notation, we have a nice way of formulating the continuum hypothesis as an equation in cardinal arithmetic. And there's a little issue in the equivalence of these two statements. It's very easy. Well, it holds in general that this statement implies this one. But to get that these two statements are equivalent actually requires the axiom of choice. Okay, and that's for subtle reasons that we'll see later in the course. So because of that, I'm going to call this the aleph continuum hypothesis. It's not normally, the two statements are not normally distinguished from each other in most textbooks, because normally one just textbooks just assume the axiom of choice and don't bother about looking at such distinctions. But I think it's worth making the distinction. So the continuum, the other continuum hypothesis implies the continuum hypothesis, and with the axiom of choice, the reverse. Okay, so this is a sort of taster of the history of set theory and this famous question that ends up being a question in cardinal arithmetic. And so in this course, we're going to look more generally at the framework of set theory in mathematics. That will allow us to understand these questions. I mean, these questions are actually fairly straightforward questions. They're going to be early on in the course, and understand much more too. As I said earlier, questions in cardinal arithmetic tend to be not that interrelated with other areas of mathematics, but set theory as a whole is very connected with other areas of mathematics. So to motivate what's going to follow in the course, and very briefly, I want to raise 4 different reasons that one might be interested in set theory and the contents of this course. So set theory is interesting because, and there are probably other reasons too. So for me, first and foremost, it is an important ingredient of many areas of mathematics, and there are many connections between set theoretic questions and mathematics. Not normally ones to do with cardinal arithmetic, but other questions like results in mathematics that depend on the axiom of choice, or very quite involved uses of set theory in subjects like measure theory, for example. So set theory is important for providing, it provides a very important abstraction, the notion of set, but also that abstraction turns out to be more subtle than you might think at first, which is how all the subtleties of set theory develop from Cantor. And there are important interrelationships with mathematics. And I'm going to, with other areas of mathematics. So part of the course is going to dwell on this. It's important for its interrelationship with the rest of mathematics. I'll just write with math. Second question, the second reason for being interested in set theory is, as everyone presumably knows, set theory is often touted as a touted means promoted as a promoted as a foundation for mathematics. Well, one way of looking at this is what happened was mathematicians needed to use sets. They needed to understand how they needed to use sets, so they needed axioms for using sets. Once they'd got their axioms for using sets, they realized that all the rest of mathematics could be defined and proved in terms of just those axioms for sets alone. And it's quite an astonishing property of set theory that you start off axiomatizing an area that's to do with building sets, and then in the end, you only need that for developing the whole mathematics. So third reason for being interested in set theory is that within set theory, one develops new areas of mathematics that crucially, that essentially then branches of set theory because they are derived from the set theory. You've got the set theory axioms that tell you how to reason about sets in an intuitive way, and those axioms lead inexorably to meaning that you can, from those axioms, derive concepts that have interesting structure in mathematics of their own. And so you get new areas of mathematics as part of set theory. So set theory leads to new and interesting areas of mathematics. Maybe I won't write them down, but such areas include cardinal arithmetic. Cardinalities are, one needs set theory to get to cardinalities. The theory of ordinals, but also theories like infinite. People that like discrete mathematics. Discrete mathematics is often done with finite structures and finite sets, but lots of the questions in discrete mathematics generalize to infinite structures, and there's a whole subject of, say, infinite combinatorics that's developed along those lines. So that's an example of an area that grows out of mathematics. And the fourth point I want to raise is that set theory also leads to a very interesting enterprise in understanding mathematics, which is almost unique to this area, and it's the area of what are called independence questions. So set theory leads to, and let's say provides the tool for studying tools for the question. I haven't formulated it very well here. I think it's better formulated in the notes. But the kind of thing I have in mind here are, it naturally leads to questions like the continuum hypothesis, that we are able to prove that from the accepted axioms we're going to have from set theory, we have a statement that, like the continuum hypothesis, and we can prove at a meta level that we can neither prove that statement nor its negation from the axioms that we have. And such questions arise naturally in set theory, but also then one wants to be able to prove that one cannot prove them from the axioms. And these proofs require a lot of technical work, and the technical work depends heavily on the tools of mathematical logic and various methods that one has for manipulating models of set theory. These kind of questions get very technical, and the level of technicality involved, it also requires a very good understanding of mathematical logic for these kind of proofs. So these proofs of independence questions are not going to be part of this course, but nonetheless we will see a lot of we will encounter a lot of interesting independent statements as we go through the course, and one important point of the course will be to somehow get a feeling for what kinds of questions are independent and why, but without the technical proof. Apart from that, the other three areas, all the other areas we'll cover in quite a lot of depth. Okay, so I think that's a good stopping point. We started late because of the technical problems, so I'm sorry about that. Because we started late, I'd like to start again on time at 15:15. So we've got an 11-minute break now. Are there any questions on? So we're going to the next part. We'll start getting technical. So this is motivation. Any questions on the motivation? Okay, so we break until 4 class. Right, so, I've just realized I didn't do something. Okay, so in this hour, I want to do the axioms that we're going to use throughout the course. So this is basically the axioms of set theory. For those of you who took Logik and Logitza in first year undergraduate, this will be more or less a reminder, although my perspective will be slightly different from that course. It'll be more strongly different from what you see in textbooks. I'm going to do the axioms set theory. From the perspective of axiomatizing sets as they're actually used in mathematics. And I'll say a few words as we go along about how this differs from what you see in most textbooks on set theory. So I won't write this part down, but just in one's mathematical education, but also in the history of mathematics, one goes through a development where the concepts that you deal with get more and more complex. So you basically start off working with natural numbers. You then move to more abstract notions of numbers like integer, rational number, real number, complex numbers. Then once in mathematics, one starts dealing with structures like pairs of numbers, so constructions on the things you've got like pairs or tuples of data, tuples of numbers like vectors, or functions. That's another construction. Then you start working with like mathematical structures where you have a set of stuff together with maybe some operations on them, like in algebra, like a ring or a field or something like that. Then you go up one step higher and you start talking about sets of sets. For example, like a topology is a family of sets, a family of open sets. And the point is, the concepts get sort of more and more involved as you get as your mathematical culture gets more developed. And we see at some point, as we develop mathematical concepts, at some point we need the notion of set. And we also realize that whereas we can start off with sets of numbers and sets of simple constructions like sets of vectors and things like that, we then need sets of sets, and sometimes we even need sets of sets and sets. So we realize that somehow we're working in a mathematical universe where we have simple mathematical entities like numbers and tuples, but we have sets in that mathematical universe, and in the mathematical universe, we can use elements of the mathematical universe as elements of our sets. So we might have a set in the mathematical universe, and then we can use it. We can use sets themselves that are in the mathematical universe as elements of other sets. So we're going to assume a background universe which I'm going to write as U. This is like the universe of everything, of all mathematical entities. And these are all the mathematical entities that we are allowed to use as elements of sets. Okay, that we may use. So it's the entities themselves that we may use have elements of sets. What is a set going to be? It's going to be a collection of elements of the universe. Okay, it's going to be some sub-collection of elements of the universe. But in general, a collection of elements of the universe we'll call a class. So a collection of elements of the universe is called a class. And one very important way to form a class is if P is, let's say P of X is a property of elements of the universe, let me write this notation, the collection for, this is defining a class as those elements X of the class of all elements of the X, sorry, class of all elements X of the universe that satisfy the property P. Okay. Is what I said. So I won't it's defined in the later code, but it's what I said. And actually we can define it like this, because an element Y of the universe will belong to the class of, okay, so this is saying, we want to talk about when does an element Y of the universe belong to the class of all X's such that P of X holds. And this holds, can somebody tell me what the right-hand side is here? P of Y. Okay. This is defining this is called kind of class notation, class comprehension notation. So you've got this very abstract universe. You know, we'll think it's got all the kinds of numbers that we have in mathematics to begin with, and vectors and things like that. It's also going to have, and once we've got the universe, we can consider collections of it, and these things are called classes. So what is a set? A set is a class that is itself an element of the universe. So it's a class that we allow ourselves to use as elements of, well, it's an element of the universe, and we would allow it to appear as an element of another set. This allows us to make sets of sets. And this is kind of a definition of a set, but it's more a definition of the terminology. So the set is a class that, as well as being a collection of elements of the universe, that collection is itself an element of the universe. That is itself an element of you. And everything would be very easy if we were simply allowed to say, why don't we just say any class can be a set? Why don't we just allow any class to be an element of a set? But there's a theorem, which is not every class is a set. Now, this theorem is known under another name, very famously, that's it's not called a theorem normally. Does anyone know what this? This is Russell's paradox. But formulated in this way, it's not really a paradox. It's just saying that we need to have a distinction between class and sets. Sets need to be special classes. Not every class can be a set. Russell's paradox. And the proof is very easy. We simply define a class R. So by the way, when I underline capital letters, what I'm doing this to say, it's a way of saying I'm considering a class here. So let R be the class of all elements of the universe. So using our class notation here, such that X is a set. So we're not saying that every element of the universe is a set. And X, if X is a set, it makes sense to ask, if it's a set, it has elements, does X belong to itself? And we'll say it's a set that does not belong to itself. And by this if and only if here, it's trivial that R is not a set, because if R is a set, then R belongs to R, if and only if the property P holds for R. This is the property P, if and only if R is a set, which we've assumed, and R does not belong to R. It's a self-contradictory definition. So obviously, this if and only if can't be true, is that we've got a contradiction. So that's a contradiction. So therefore, this class is not a set. So we've shown that not every class is a set. Okay, so Russell's paradox merely says we need to have a distinction between classes and sets. And this is where the need for axioms of set theory comes in, because if there's a distinction between classes and sets, well, it's very easy to define classes. Any collection is a class. But if not every class is a set, well, which classes are we going to allow to be sets? So we need axioms to tell us which classes we're going to allow to be sets. And all our axioms are going to be of the form: the following specified class is a set. Okay? Our axioms no, one axiom is not going to be that. Our axioms will tell us which classes can be sets. But before that, we need one other axiom, which is of a different nature, and that is the axiom that tells us what equality between sets means. And this is the axiom of extensionality. So the first axiom, which is actually not of this form, the first axiom, extensionality, tells us what it means for two sets to be the same. So X and Y are sets, then and they have the same elements, and for all Z belongs to X, if and only if Z belongs to Y. By the way, an unbounded quantifier like this is always a quantifier over the universe, U, of all entities that might belong to sets. So then the sets X and Y are equal. Okay, so that's our first axiom, just telling us that it's just consistent with the idea that sets are collections. A collection is determined by power. So one way I'm going to now depart from treatments in from standard textbook treatments is I'm actually going to strengthen the extensionality axiom to extensionality for classes. Classes are themselves collections. And so it's reasonable to say if X and Y are classes, So I'm underlining them. So we're talking about classes, and they have the same elements, then the two classes are equal. Now, people that have a very formal logical approach to set theory, which is the majority of books of set theory, in which set theory is a first order theory in which variables range over steps. In that setting, which is the standard one for set theory in most textbooks, this axiom cannot even be formed. Okay, so there's this axiom is in the sense going to be the biggest mismatch between the way I do things and what's in the literature. It shouldn't cause you any problems. And so it's just convenient to have this way of thinking about classes. It just doesn't quite fit in very easily with the usual first order framework of set theory. Everything else fits in very comfortably with the usual first order framework for set theory. This course is going to be presented from a mathematical rather than a logical point of view until the last lecture. And in the last lecture, I'm going to go into formal. Only in the last lecture, we're going to look at the formal logical side of that. Okay, once we've got extensionality classes, so we then start off with the axioms that tell us that specific classes are sets. The axioms I'm going to give are, some of them are redundant. We can derive them from each other, but still each one says something in its own right. So I think this is a nice collection of axioms I'm going to present. So the first one, so this is the first axiom of extensionality. The second axiom is the empty set axiom. But this simply says the empty class is a set. So the empty class we can define like this. This is false. So the set of all elements X of the universe satisfy false. So sorry, not the set, the class of all elements of the universe satisfying false. The empty class is a set. As I say, all the axioms are going to be some defined class is a set. And of course, we're going to give ourselves notation for this. So this is the standard empty set notation. The next axiom, so the first couple of axioms allow us to build small sets. This is the empty one. We could have an axiom to build a singleton set for any element in the universe, but we don't need it because we're going to derive that from the next one, which is if we've got any two elements of the universe, we can put those two elements together in a set. So pairing is then, the pairing axiom as it's called, is for any xy in the universe, the set of z such that z is either x or z is y. So this is the set. So this is the class of those z's that contains exactly x and y. So if x and y are different from each other, it contains two elements. If x and y are the same, then it contains one element. This is a set. And again, we'll introduce the standard notation for this. Define this class. You've got this class, which is axiom-totally set, and give it the notation for the unordered pair. And using the pairing axiom, we can define the singleton by the singleton set is just the pairing of x with itself. Okay, and it has one. Okay, so we've got empty set pairing. So I should have said, it's said in the notes, there are various motivations for these axioms. So we want to say when a class should be a set, we should have some principles by which we which we're following to say when a class is a set. So there are kind of three related principles that are mutually compatible. Some people emphasize one and other people emphasize another. But the three basic principles are, you might view sets as those classes that are kind of small, in a sense. The universe is very, very large, but the sets are sort of much smaller than the universe as a whole. So the empty set is as small as it can be. Pairing is a pretty small set too. I mean, having said that, when we start developing the axioms for set theory, we're going to show that we can construct from our axioms some very enormously mind-bogglingly large sets. So there will nonetheless be large sets, but still, however large a set we construct, it is still going to be very small in comparison with the size of the universe as a whole. Anyway, so one intuition for a class is a set if the class is somehow small. Another one is a class is a set if it's somehow definite in scope. So you can think of the universe as a kind of very open-ended thing. You know, it's all the mathematical entities out there that we might allow ourselves to put in a set. But these kind of collections here, these are not open-ended at all. I mean, this has nothing in it. This has exactly two elements. And in general, sets are going to be like kind of quite definite in scope rather than open-ended. And the third intuition is that you might consider a set to be something that you construct from other sets by kind of building up a larger set from smaller sets that are its elements. So here we constructed this set out of nothing, and here, well, we've got two elements, and we construct the set from elements already given. So and there's a precise way of formulating this called the cumulative hierarchy, which we'll get onto later in the course, but just to have those three intuitions to hand. Okay, so that's two axioms. I need to remind myself of the order of. Okay. The next axiom is the union axiom. So for a class, so this is a side definition, for a class X of sets. So by a class of sets, I mean a class in which every element in the class is itself a set. We define the union of the class to be set of all elements. So the elements of X are set, and we consider the set of all elements of X. And the set of all Z, such that there exists a Y, and well, every element of the class X is a set, so let's put the capital Y there. There exists a capital Y in X, such that Z belongs to Y. So that's notation. And another side remark. So another difference between what I'm doing and the way most textbooks on set theory work is that I'm starting off with this universe that contains other mathematical entities like numbers and tuples and functions and things that might just be given beforehand before we even consider the abstraction of the notion of set. Most books on set theory just work in the universe in which everything is a set. So they would never need to say if you have. They often don't use the concept of class either, but they would never need to say if you have a class of sets or a set of sets, because any class is a class of sets and any set is a set of sets. So I prefer to work in this framework in which we do allow ourselves to have other primitive mathematical entities, because it kind of corresponds to mathematical practice. As it turns out, it doesn't really make any difference, and we'll see precise statements to that effect in the last lecture of the course. But for the moment, we'll fit in our framework where potentially our universe contains things that are not sets. So sometimes we need to say we want to define the extent of the union operation. It's incumbent on us to say if we want to form a union, well, we can only form a union of a class, but it's a class of sets. And this, of course, is the class. The union of class is a class. But the union axiom is if X is a set of sets, then the class that's the union of X is itself a set. Okay, so if you've got a set of sets, you union them all together, you get a set. Very intuitive. So then we've got the power set axiom. Again, we need some notation before that, which is if X is a class, we're going to define power class of X to be the class of all Y, where Y is a subset of X. So what this means is Y is a class and Y is a subset of X. And I won't write out the definition of this, but you know what this means for all Z in Y, Z belongs to X. Okay. So this is notation here. So this is the power class of X, if X is a class. But importantly, it's the class, it's not the class of all subclasses. We can't do that because they're only, our elements of the universe only contain those classes that are sets. That's the qualification, that's the definition of a set. If you're a class that belongs to the universe, you're a set. So all we can collect here into this class is subclasses of X that are set. Sorry, this should have said set. Yeah. Sorry, set. Okay, so the power class is the class of all subsets of the class X. And in the case that, well, and the power set axiom is if X is a set, then the set of all, then the class of all subsets is itself a set. And then P of X is a set. And in this case, because it's a set, it's reasonable to call it the power set. In this case, we call P of X is power set X. There are two more axioms, separation, and maybe we'll go on to the other board. Separation and replacement. So separation says if we've got a set, and we single out some elements by applying a property to the elements. So if X is a set, and P of X is a property of elements of the universe of U, then the class, which we'll write like this, so this is, if we didn't have the belongs to X here, this would be the class of all elements of the universe that satisfy Px, and that could indeed be a class. But if we restrict to those elements of the set X that satisfy the property, because we start off with a set here, we've made it smaller, because we're just singling out some of the elements of X. So by the size intuition, it's reasonable for this to be a set. And the axiom says that that is indeed the case. Okay. And then replacement. So this is subclasses of sets are sets. And replacement is a kind of dual axiom for if you've got a set, then you apply a function to it, and the image of the function is again a set. So this is formulated as follows. So if X is a set and X Y is a property, let's do it like this. F is a class function from X to the universe. Then the image of that. So the idea here is we have a function mapping all the elements of X to mapping every element of X to an element of the universe. And once again, because we start off with a set here, the elements of the universe we hit, we're kind of, again, making the set smaller, if you like, because we might be identifying sending several elements here to the same place here. So the image here in the universe is no larger than X. Again, by the size intuition, it's reasonable to call this a set. Now the image F is, again, which is a class, is a set. Of course, I should really tell you what a class function is. So let's formulate that. So we can consider, as usual in mathematics, functions as specified by relations that enjoy two properties. One is that they're single valued, and the other that they're total single valued relations. So a class function from class X to a class Y is a property relation, if you like, on the universe fxy is of elements xy u, satisfying it's functional, so it's single valued and total. So for all x in class X, for all little x in the class X, there exists a unique y in little class Y, in the class Y, a unique little y in the class Y, such that f of x, y. And lastly, just so it kind of makes sense, if f of xy holds, then both f only applies to elements of the classes x and y. Okay. And then the image of a class function is defined to be it's the class of all those elements in the codomain y for which there exists an element in the domain such that y is hit by a function. Yeah.
But it seems to me that it will be like more this formulation, more analogous to how it's usually done. We replace X there with just the universe.
No, which X?
This X here, so we have X from the universe to the universe, and then we have the image of
Here.
Yes, restricted to X.
It doesn't make a difference.
Yes. I agree that both are.
Yeah. I mean, the way I formulated the axioms is a bit different from, in many ways, from how they usually formulate it. But modulo the issue I said about extensionality for classes, it's equivalent to the usual formulation. Okay, so these are all our axioms for set theory, apart from two. So they're not all the axioms of ZFC, because ZFC is the Mello-Frankel set theory. I'm going to talk about that in the last lecture, but the Mello-Frankel set theory is in a setting in which all classes are, in which all elements of the universe are sets, and in which classes satisfy, which sets satisfy a property called foundation, which I'm not going to have at all. And there are two axioms from power development that are missing here. One is the axiom of infinity. I haven't said anything, so we don't have an axiom of infinity in the third hour. And the other is the axiom of choice. And the axiom of choice we're going to leave until later in the course. And apart from that, this is all the axioms. And with these axioms, I want to start to develop some mathematics now. Now I'm going to go at quite a pace for now and the remaining hour, because I want to today cover quite a lot of material. The point is to get this out of the way. It's all stuff that one could do slowly, but then it would take a long time to get anywhere on the course. It's all sort of background stuff that you can kind of get up to speed with the details over time. You don't need to understand everything right now during the lecture. The lecture notes are also fairly detailed, so you can look in the lecture. But I want to get through a good amount of material of what we can develop from these axioms alone, leading to, at the end of the lecture, the axiom of infinity. So to start with that, the first thing I'm going to do is to show from these axioms how one gets products, finite product of the product construction on set. So you may remember from those of you who took Logica and Logica, you may remember how to construct products as Kuratowski pairs, products using the Kuratowski pairing operation, which is one way of doing things. But the style I like to adopt in this course is a bit more modern in style. So I want to do things like this. I'm going to define what a product is. And first, we're going to define product of classes. So I'm going to, one of the things in my treatment of the material in this course, I like to have classes as a means of discussing, sort of formulating the axioms, and a useful concept to have available. So we're going to first talk about the product of classes. So and rather than telling you how to construct a product, I'm going to just define what it is to be a product. So a product of two classes is a class which we write as x times y, together with two functions called the projections. So class functions, the projection 1 goes from x times y to x, and projection 2 from x times y, satisfying the property that for all pairs of elements, a little x from the class x and a little y from the class y, there exists a unique element Z of the product that represents that pair of elements. What does it mean to represent the pair of elements? So there exists a unique Z in the product structure, X cross Y, such that, well, if there exists a unique, I said it, but I didn't write it, so I use the standard notation for there exists a unique with an exclamation mark here. So what does it mean for Z to represent X times Y? Can anyone complete this? Yeah, that's right. So such that the projection, first projection Z is X, and second projection Z is Y. And the reason for giving this definition is in mathematics, when one has products of structures, this is what you need to know when you have a product to deal with it. You don't want to know that you have a product where the elements are Kuratowski pairs of constructed as Kuratowski pairs. That's got absolutely no value, mathematical value at all. So this is all we need for a product. And it's a proposition that we have two different products, so different representations of the product, different, you might have one class and another class with different projections on it, but they'll be isomorphic to each other. So any two, so I'll just write it down informally, but it's written precisely in the lecture notes. Any two products are of X and Y are isomorphic, meaning there's a bijective correspondence between them, bijective class functions, and moreover, there's a homomorphisms with respect to the projections. They respect the projections. So any two products of X and Y are isomorphic. So I think this is a more modern style of doing mathematics than coding things up by a direct construction. But one still needs the direct construction because all I've done here is defined what it means to be a product. We still want to know that products actually exist. So from our axioms, we can prove that there exists a product. And for that, we need to construct a product. So that then becomes a theorem. So theorem of every X and Y classes a product X times Y together with projections exists. And proof sketch. The details are in the lecture notes. We simply define, this is where we decide how we're going to code the product, and Kuratowski pairing is the neatest way of doing it, in most people's view, which is why everybody uses it. So I'll write sub K. Just to say we're representing, so we're going to define sub K Y. This is the sub K here just means, well, who cares about it? It's in the notes anyway, but the sub K means it's going to be defined using Kuratowski pairing. And this is, we're going to define this class as the class of all Kuratowski pairs of elements little x from X and little y from Y. So it's the class of all elements of the form. So the Kuratowski pair of little x of X, Y is defined as the the potentially two element set that contains the singleton little x and the doubleton little x little y. Although in the case that x equals y, it's just these two are the same thing, and it's just a singleton containing a singleton. But anyway, it's a neat definition, a neat way of coding up a pair. So it's the class of all such sets of this form, defined using the pairing axiom twice to get that this is a set. But x belongs to x and y belongs to y. And the first projection of the z of this form, because it's the class of all things of this form, is defined to be so this is defined to be the unique x in x such that there exists a y in y such that z equals x and y. So this is defining a relation between element z of the universe and elements little x. And I've rubbed out the definition of class function that you need to then prove that this satisfies the properties of the class function, and that requires a little bit of thought, and it requires even more thought for the second projection, which I'll let you fill in the details. But the point is, we use the Kuratowski, the construction of pairs as Kuratowski pairing, a particular set theoretic definition, to prove that a product structure exists. From now on, we're going to forget that we define products in this way. And when we use products, we'll always use just a defining property which characterizes them up to isomorphism. Yes?
X, comma, X. Why do we define the?
So like this.
Yeah, what would be the problem?
Yeah, you don't know which is the first element and which is the second element. So defining all the product is ordered pairs. You need to know which is the first element and which is the second element. And this is just a set with two elements, and they don't have any. 2, 3 is the same as 3, 2. So, yeah, a good question. And lastly, last proposition. So we don't need an axiom for this. It follows from, for example, you can prove it from, well, maybe I'll tell you why it follows, or one reason. The proposition is if x and y, but it also just follows from the abstract characterizations, are sets, then so is x times y. So in our case, you can think about it. We need to derive that this class is a set from the axioms we've got. Each of these elements is sets, but that's not enough. But here we're essentially unioning over two sets, x and y. Anyway, the argument's in the notes, just to say it's an important property because obviously the product of two sets should be a set, and that follows from the axioms. Right, it's 5 past. So again, I'm sorry, because of the delay at the start of the lecture, we're going to have a 10-minute break and we'll start again at 15:15. Hopefully in future weeks, we're not going to have the technological glitch at the beginning and we'll be able to have more leisurely breaks. Are there any questions? Right. Okay, so the first consequence, mathematical consequence of the axioms was the construction of product, two classes. In product of two classes, we can start using it. So suppose we've got a class function from x to y, because we've got the product, we can define its graph. This is a class function. This graph. So, graph of that. Underline it because it's going to be a class. So this is set of pairs with x, y, in times y, such that y f of x. Of course, now I defined a class function as a binary relation. But you know what I mean. You know, here if you think of it as a binary relation, say f of x comma y. But I'm going to use standard notation, function application, of course. Okay, y equals f of x. So this is a subclass of x times y. So the collection, a subcollection of the product class. But in the case that x is a set, x is a set, and f from x to class y function, it's a class function, then the graph of f is a set. And that's not obvious because the product x times y is a product of a set with a class. And of course, the reason is that the y is determined by x. So you can use replacement. You can define another class function which maps from x to the product x times the class y. And given little x returns little x paired with f of x. And its image is the graph. And because it's the image of a class function from whose domain is a set, by the replacement axiom, the image itself is a set. And this is by replacement. And because when the domain is a set, the graphs are, the whole function itself can be represented by a set of data, so to speak. We'll omit class in that case, even I'll just call such things functions, even when the codomain y is a class. I mean, the codomain y is a class, but the image, nonetheless, within y is a set because we've got by the replacement axiom. And then, because the graph is a set, we can define a class of all functions from x to y. So we can define an exponential class where we're exponentiating a class y with an exponent x. So this is the class of all class functions from x to y. So this is collection of all graph of f from x to y is a function. And we can do this because we're forming a class. So for a class, we just need to single out some elements from the universe, but these graphs are indeed elements of the universe because the graphs are sets. Okay. And then, this is the proposition. Let's say I don't remember in the lecture notes. Proposition, if y is a set, then class of all functions from x to y is unsurprisingly again a set. Y to the x is a set. Now, in this case, we don't need some of the complicated arguments we had before, because if X and Y are both sets, product is a set. And so the graph is a subset of a product, which is a set. And then the set of all functions is a set of subsets of the set, which is the product. So it's a set of subsets of the set, which is a product. So it's a subset of the power set of the product. So if it's a subset of the power set of the product, it's an element of the double power set of the product. So using the power set axiom twice, you get that this is a set. Okay. Actually, arguments like that, I've realised are not in. I said the lecture notes were detailed, but those arguments about things being a set are not in the lecture notes. But I think we will do some arguments like that in the exercise class. In the lecture notes, I have a different presentation of exponential sets and classes. Again, along the lines that I use for products, where we define them in an intrinsic way to do with characterizing what an exponential is up to isomorphism. So a more modern style, rather than giving a definition. But as a shortcut in the lecture, is we needed to go through these definitions anyway. I thought I'd just give you this. But have a look at the lecture notes for a more modern style of presentation. For the remaining part of the lecture, I want to do the last bit in the more modern style. And the last bit is going to be about the first infinite structure of interest in mathematics, which is the natural numbers, where because we're not analysts, our natural numbers will contain zero. I don't know how common it is in the, be interested to know to have a division of all courses and on the mathematics degree, those in which zero is a natural number and those in which it's not. In our course, zero is going to be a natural number. And what are the natural numbers? So one answer is we've got sets, would be to encode the natural numbers as sets. And again, if you did logic and logic there in the first year undergraduate studies, you might remember you start off with the empty set, and then you have an operation that given a set representing a natural number generates another set representing a natural number. And this is like the Kuratowski encoding of pairs. It's encoding a natural number as a particular set theoretic structure, and it doesn't have anything to do with how the natural numbers are used in mathematical practice. So from a more modern perspective, let's just, we're sort of, the way I was motivating the axioms is we start off with our universe of mathematical entities, and we include sets alongside the existing mathematical entities. And so we might expect numbers to be among our, we don't have any entities there, numbers ought to be there. So we might have some already given set of things we're calling, a collection of things we're calling natural numbers. So let's just give ourselves some basic axioms for what a natural number structure should be. So for us, a natural number structure so this is the sort of thing you will not find in any books on set theory, but it seems to me the right way to do things. But let me remind myself of exactly what the definition I've written in the notes is. So it's a triple. So n, the natural numbers. And to begin with, I'm just going to assume this is a class. We want to have some natural numbers, but we won't yet say that they form a set. You can put them in a different order, a 0 and an S. So where n is a class, 0 is an element of the natural numbers. It's going to represent the number 0. And S is class function from the natural numbers to itself. And this is going to be the successor operation, adding one, satisfying three properties. Firstly, S is injective. So in other words, for all X and Y in the natural numbers, if S of X equals S of Y, then X equals Y. So what I call acyclicity which is for all X in natural numbers, the successor of X is not zero. And thirdly, the induction property that we all know and love from the natural numbers. So if X is a class and satisfies the properties that zero belongs to X, and for every little x in the class X, the successor of little x also belongs to class X, then what can we say in this case? Oh, sorry, this doesn't even make sense. This should be, well, the successor only makes sense for natural numbers. So for all X in the natural numbers, if little x belongs to class X, then the successor of X also belongs to class X. Then what should we be able to conclude from this? Yeah, although we're not assuming the natural numbers are a set at the moment. So the natural numbers are a subclass of X. Okay. So that's a natural numbers structure. And the maybe surprising theorem is, or I don't know if it's, let me check if it's a theorem or a proposition. It's a in the notes. So I tend to call things theorems if I think they're a sort of significant fact, and I call them a proposition if it's just a fact to know. And now I can't even find it. Well, anyway, I shall check the notes to make sure it's there. But anyway, the theorem, let's call it a theorem, is that from our axioms, even though we don't have an axiom of infinity, a natural numbers structure exists. And the proof is not done in all details in the notes, but it's done, quite a lot of detail is given, and it takes about 3 or 4 pages of LaTeX proof, proves that this exists. But the idea is construct class M as the class of von Neumann natural numbers. Von Neumann natural don't remember how to spell monoidal, so I'll just put VN, natural numbers. So this is the natural numbers as I described before with the encoding. Where 0 is the empty set. We can represent numbers as sets. 1 is the singleton empty set. 2 is the doubleton that contains is the elements of the empty set and the singleton empty set. And there's a natural way of sort of inductively generating those. And one can define in the language we've got, one can define the class of all sets that are generated by that pattern. And one can prove from the axioms with no axiom of infinity that that class is natural number structure. Okay, so I may give some details of this at the end, but I want to cover the other material first, and then, if time permitting, we may come back to some of the details of how one constructs this proof. But the point is, again, the proof is a square to mark the end of the proof. The proof is construct a particular structure using a representation, but in mathematical practice, we'll never be interested in that particular representation. Do mathematics, what we need are these properties of a natural number structure. So from now on, apart from at the end of the lecture, time permitting, when I may do some details of this proof, but apart from that, from now on, we will just work with these axioms here. So the first proposition, so forgetting the concrete encoding of the natural numbers as von Neumann natural numbers. The first proposition, which again is precisely formulated in the lecture notes, is that any two natural numbers are. It's actually not the first proposition. I was going to say any two natural numbers objects are isomorphic to each other, which is true. But to get that, we need a theorem, which is a very important theorem. So let's take a little bit of time illustrating this theorem. This is called the recursion theorem. So this theorem says that the natural numbers are, well, the inductive property gives that essentially that we've got a class here containing 0 enclosed under successor, and by these first two properties, we get infinitely many different elements in that way. It's just a little bit to prove. There's not totally immediate from those, but it follows. And then the inductive property says those are all the elements we have in the question. The recursion theorem says, well, then if we've got any other structure that can, and we pick out an element of it, and we've got a function, an endo function on the structure, then we can define we can use those elements to define a sequence that's iterating that function on the starting element. So it's basically saying this is the initial structure, the initial class with a distinguished element 0 and an endo function on it. So that, let's keep the notation the same as in the lecture notes. So given a natural number structure, I won't write that part. Suppose A and this is a class F in A. Let's put it the other way around because to make it consistent. Are such that A is a class, little a is an element of the class A, and F is a class function from class A to itself. Then there exists a unique class function, which I call R, from N to A, such that R of 0 is little a, and R of successor of x is f of R of x. So what it's saying is a unique function from the natural numbers that gives us, function from the natural numbers you think of as a sequence, an infinite sequence, and it gives us the sequence that is iterating iterates of the function f applied to the starting element for a. Okay, so 0 gets mapped to a, and every 1 gets mapped to f of a, 2 gets mapped to f of a, and so on. Okay. And this follows from this definition, but once again, it's not very straightforward. So depending on how much you like or you don't like these kind of things, this is not material that's going to be examined, but you are welcome to browse the proof in the lecture notes of this, and it takes a couple of pages to prove this result. There's some nice ideas in proving this, but I don't want to spend a lot of lecture time on this sort of basic material. That's the recursion theorem. And once you've got the recursion theorem, it's then easy to show that any two natural numbers structures are isomorphic. Because suppose you've got two natural numbers structures. So one is this one here, and the other one we'll call that one, we'll call class A, little a, and f, that's our other natural number structure, and we get a function from one to the other by this result. But because A is also a natural number structure, the same result applied to that natural number structure gives us a function in the other direction. So we've got functions from one to the other and back, and the composite of such functions, of those two functions, needs to be the identity in both cases, because it's the unique function that preserves the 0 and preserves the successor. That's basically the idea there. Point is, two natural numbers structures are isomorphic. There's a slightly more general version, which is called the parametrized recursion theorem. So let me just generalize this. And I don't prove this, but the proof is actually basically the same as the proof of the original version, but just with a bit slightly heavier notation. So it's nicer to do the proof in the simple case and note it and then observe generalizers. But the parametrized recursion theorem is that we give ourselves a parameter class Z, and we'll allow A to also be given by a function. Little a can also be given by a function. And then there exists a unique R from parameter. So it's basically doing the same thing parametrically in another argument, little z. And we have R of little z0 is A of z. And R of little z S of x is f of little z. F z R x. It may look a little bit mysterious, but essentially we're just sticking a parameter argument in there. And to see why that parameter argument is useful, let's consider an example. So we're going to consider the example where A is going to be the set Z, well, the class of Z. Sorry, what did I say? A is going to be the natural numbers. Z is going to be the natural numbers as well. In the lecture notes, this is given by a B here rather than, let's make it consistent. So capital B is, yep. So our starting data parametrically in Z is now given by the function B. And B from, so Z times A to A from N times N to the natural numbers is, sorry, so B from, thank you. B from Z to the natural numbers, that's a natural, from the natural numbers itself, B of Z is Z, and F of Z, F of Z of X is S of X. So then there exists a unique function R. So there exists a unique, so by the parameterized recursion theorem, there exists a unique function R from Z times N to A, which is N times N to N, such that R of Z of 0 equals B of Z. So R of Z of 0 equals B Z, which is Z. And R of Z of S of X is F of Z of R of Z of X is F of Z of R of Z of X, which is the successor of the right-hand side, which is the successor of R of Z of X. So now if we've got a unique function from the pairs of natural numbers to natural numbers satisfying these two properties, but we can hopefully spot a function that satisfies these properties. Can anyone see a function that satisfies these? So we can say a function R in two arguments on the natural numbers such that if you combine it with 0, you get the first thing back, and if you combine it with a successor, we get the successor of the combination. Addition. We can see that Z plus 0 equals Z, and Z plus the successor of X equals the successor of Z plus X. So addition satisfies this, and so therefore this must be addition because it's the unique function that satisfies it. So we've used the parameterized recursion theorem to define addition. Okay, it's not very exciting to define addition, but once we've got addition, another application using addition gives us multiplication. Another application using multiplication gives us exponentiation, and we're sort of off and away and being able to start doing interesting things with the natural numbers. So this theorem is very, very useful. Right, so we have a okay, so we've got the theorem. There exists a natural numbers structure. What's missing about this natural number structure? I mean, from it we can already do arithmetic and stuff, but what
We want it to be set.
we want it to be a set. So we cannot prove from the current axioms that it is a set. So this is where we need another axiom, and the axiom of infinity. But yes, of infinity, one would really like to write it as a specified, all our other axioms apart from extensionality, but all of the form, a specified class is a set. It'd be nice if we could say that a specified class is a set. We could say our natural number structure is a set, but that's a bit awkward because our natural number structure is only specified up to isomorphism. But actually, if you want to say a specified class is a set, it is quite useful to be able to define a specific natural numbers structure. And so, in addition to using a specific definition of the natural number structure to prove a natural number structure exists, it's also quite handy to have it now for the axiom of infinity. I want to say the von Neumann class with the von Neumann natural numbers is a set. So how do we define? So this is now going into the proof of the theorem, but also if we can use it in the axiom of infinity. How do we define what the von Neumann numbers are? So a class is a Vn number if so. And now, sorry, a set. So Vn is going to be the class of all Vn numbers. So a set is a Vn number if, well, the idea with the von Neumann numbers is that they are the empty set, and the singleton empty set, and empty set. And if for every number n, for the successor we take, it's a set, and we take that set union the singleton of n. So this is like a successor operation. So for a set Z, we'll define, or for a set n, we'll define n plus. If n is a set, the successor of the set is defined to be n union singleton n. Whoops. Okay. The point is the natural numbers, the von Neumann natural numbers for n always is a set, always with n elements, and those n elements are always the von Neumann numbers, but it's the set of all von Neumann numbers for all the numbers strictly less than n. So that 2 is the set of 2 elements where those are the von Neumann numbers for 0 and 1. And 3 would be the set containing this, this, and this. But how do we define abstractly what it means for a set to be a von Neumann number? One way of doing it would be to use the notion of well-foundedness, but we haven't done that in today's lecture, and you maybe don't remember it terribly well from Logik im Noschitzer. So we're going to have 2 properties. So if the first property is satisfied, that is for every subset, so set X is a von Neumann number. If for every subset, I mean, you're not going to need to remember these things, just to show you that you can code up what it means to be a von Neumann number. So we want it to satisfy a kind of induction property, which is that basically it is closed under induction as far as you stay within elements of the subset of the set X. So if the empty set belongs to X, then it also belongs to Y, and for all Z belonging to Y, if Z plus belongs to X, then Z plus, when this is the plus operation, belongs to Y. Let's draw a boundary there. So whenever this sort of induction property holds, it holds that Y equals X. So basically, any subset of X any subset Y of X that contains 0 whenever X contains 0 and is closed under successor as far as X contains the successors, is the whole, any such subset Y is the whole of X. And secondly, every element of X is either 0 or a successor. So for all, so X, I mean, in fact, it's just for X itself. X is a von Neumann number. For it to be a number, it needs to be either 0 or a successor. So either X equals 0, or there exists a Z in X such that Z is such that X is the successor, that X is the successor of Z. So it's a bit cumbersome, but it works. And then Vn, the class, is defined to be the class of all Vn numbers. So in other words, class of all X is the set, and Vn being the Vn number entails being a set, the Vn number. Okay, so, but then with this formulation, you realize that the axiom of infinity in this form is quite a horrible thing to write down. So it's a very long-winded axiom to actually write. So nobody ever writes the axiom of infinity like this. In fact, if you're dealing with another Fraenkel set theory in which everything is a set and another axiom called the axiom of foundation holds, the property of being a von Neumann number can be simplified quite considerably. So that's a nice thing about the standard formulation of set theory. But what we can do instead, which is what's often done, is in order to have an easier to state axiom of infinity, we relax a little bit the requirement on our axioms. So the axioms so far, apart from extensionality, have all been of the form a specified class is a set. This version of the axiom of infinity is the same. A specified class is a set. But an easier way of stating infinity is just to formulate some class that's not uniquely specified, but has enough properties that force it to be infinite, and just say that's that. And that's actually quite easy to do, because one can simply say, so this is the form of the axiom of infinity. We adopt instead the equivalent formulation. Equivalent, but more concise. Concise formulation, which simply says there exists a set X, which is forced to be infinite because it contains the empty set, and for all Y in X, Y is a set. Y in a set implies the successor of Y, also the von Neumann successor of Y belongs to this. There exists some set X that contains the empty set and is closed under von Neumann successor.
Remind the foundation prove that the successor operation is rejected.
Yes, you do, but that doesn't matter. So the successor on this set might not be, on this class here, oh, sorry, this set X here, might not be injective, but it doesn't matter. Amongst its elements, it must contain all the von Neumann numbers, and the successor is provably injective on the von Neumann number.
Okay.
So for this, we're just saying there exists some set like this. If there exists some set like this, there exists a subset of it, which is the von Neumann numbers.
Okay, but
and you can prove that the successor is injective on von Neumann numbers from these properties. And that's in the lecture notes. or the statement is in the lecture notes. I don't know if the proof. Maybe it's not. Oh, proof exercise, lemma 2.11. There you go. That's a good exercise. Anyway, so in the end, this is a nice, concise formulation of the axiom of infinity. Doesn't matter, it's equivalent to saying this precisely defined class is a set. Okay, so that's the end of today. So it's been, they started off with more philosophical stuff today and general discussion. In terms of material, there's been quite a rush of material. The point was to get these basics down. You don't need to understand all the details about the proof stuff, how to prove these things. It's just from this point on, we'll be kind of working in the framework of ordinary mathematics together with the set theory axioms. For those of you who are interested in how things are working beneath the scenes, read the lecture notes. The exercise class will cover some of the proofs anyway. But from next week on, the style should be a little bit more relaxed, and but we'll be, we're in a position now that we've got the basics and we can start doing interesting stuff with set theory. Are there any questions? Okay, so thank you very much, and see you next week.